Basil, let me know when you have to start, okay? I can start presenting at
So we
that
can
time.
start at 5, sir.
Oh, okay.
Hi everyone, welcome to today's webinar on autonomous vehicles. We are proud to introduce our speaker, Dr. Ramakrishnan Raja, the Chief Scientist of Motor Drive Controls in Halla Mechatronics. Over to you, sir.
Hello, everyone. Thanks for the opportunity. Let me give you a small introduction of what I do. I am basically working in the area of steering and brakes and traction drive for Halla Mechatronics. We are like a tier one supplier for various OEMs. So I've been working in this area for 20 years, 18, 19 years now, for in the area of motor drives and controls. So today's presentation is going to be a little different. It's not going to be in the area of motor drives, but it is going to show you about the advanced safety architecture, um, which is happening in our industry, especially with autonomous vehicle, and how does the safety architecture implies, and how is that integrated when we design motor drives and when we design motor architecture, and what is the importance of safety and all that stuff, and what is changing in our industry, because right now there is a lot of change due to autonomous, how safety is integrated when we design each and every part. So we are going to go about that today. So let me share my screen here. Can you guys see my screen?
Yes, sir.
Okay. Um, so the topic here is about advanced safety architecture in automotive. Today we will be going as an agenda wise, showing what a safety system means, and what all different levels of autonomous is there today, and what all we do for meeting the safety and autonomous level. What is the connection between safety and autonomous level? And also starting to do with design concepts, which one of the design concepts is redundant design concept. Then there is, we at the end of the presentation, showing various design concepts available. We'll also go about the future trends in automotive, in the architecture wise, which is called steer by wire and like brake by wire example. So we'll be going in those, touching those architecture concept also, and what changes from a controls perspective as well as from a design perspective, what all are changing and why is it useful. That's the main concept here. I've kept this presentation in the level where I'm trying to introduce this concept. I'm not trying to go behind too much technical or too much math and stuff, but I'm trying to introduce this concept to understand the point of what safety and what autonomous is changing in our industry from an architecture perspective. So starting, we know that from early 1950s to presently in cars, various different safety features. We have ABS, we have airbags, a lot of things have changed. But 2000, after 2000, it's been pretty constant and there's no much advancement. But lately, there's a huge lot of change in the safety point of view in the vehicles. And it's not evidently seen in a vehicle when you buy it, but in the design wise, in the architecture wise, there's a lot of changes. So before I start on what all changing, what is safety critical system means? A safety critical system is a system whose failure or malfunction may result in one of the possible death or loss of severe damage to equipment, environmental harm. So these are called safety critical systems. So in a vehicle, there are a lot of safety critical system. There are key safety critical systems which we have to worry about. And those are basically the brakes, power steering, traction drive, if it's an electric vehicle, and throttle control system. So these are preliminarily considered as safety critical components in an automotive industry. So the area where the safety is integrated to make sure that we have a good safety critical system is on these areas. So I'll be taking power steering as an example in this presentation too. So there are different operation mode of a safety critical system. And mainly, there are different types, and already when we look at today's present vehicle, there is a way when something fails in our system, how we react to that failure. Usually, to give you an example, if a steering fails in our system, if a power steering fails in our system in a car, today we go into something called manual steering. That means the whole power steering is turned off and the driver will be doing manual steering. So that is one type of reaction to the system. These kind of reactions which we have today based on a failure, is all changing today because of autonomous, because we cannot just turn off the system, because when we go autonomous, we need to have multiple redundancy or safety analysis. So we have split safety critical system into basically 4 buckets. One is called fail safe system. That is a system that goes into a safe state when they cannot operate. That is, either they can shut down, that might be a fail safe state for that system. So that's all fail safe system. Then the other one is called fault tolerant system, where a faulty behavior of one or more system does not lead into catastrophic malfunction of the overall system. That means a system failure, one failure cannot take down the whole system or lead to other system failure. That's another type of system. Fail soft system, a system is able to continue to operate in interim basis with reduced efficiency. That means it's not turning off, but it will reduce the performance and it can still continue for some time. The fail operational is where the system continues to operate even when there is a failure. That means a driver wouldn't even know that there is a failure happen, but he can keep continuing. There'll be a warning at the end of it, but there is no performance degradation, nothing happens. So if you look at this 4 type of safety critical buckets, you can see that if you drill down, you will have to design your motor drives, you have to design your power electronics in such a way that it will satisfy either a fail safe or a fail operational system. Now, in traditional system which we have in vehicles today, if there is a single point failure, say a sensor failed or any single point failure in a system, taking the example of say traction drive or say steering, if a torque sensor failed or if a current sensor failed, we immediately shut down the system. This strategy is what been applied in most of all the systems we have in our vehicles we have today. While this strategy doesn't satisfy the future needs of automotive. It was okay till now until autonomous starts to kick in. Now, that's where we have different types of automation in our vehicle. There are level 0 to level 4, and I know there's a level 5 coming up now. But in majorly, if I put autonomy level into 4 levels, level 0 is what we call as no automation. We have all our vehicles today has this. That means there's no steering, braking, throttle control. That means only a warning. If something fails, there's a warning and we'll shut down the system, like crash warning system. Level 1 autonomy level is basically function specific automation. That means a braking, so take a case of ABS. When you have ABS in your vehicle, when you brake hard, it's only a braking which it does its own braking during a sudden braking condition, which ABS does. But it doesn't have multiple cross functionality. That means braking doesn't talk to steering and all that stuff. So and it doesn't talk to throttle. So it's a specific function. Like if you take brakes, there is some level of autonomous when in certain condition. That's what we call as level 1. Now, level 2 is what we call as the adaptive cruise or combined function automation. In the newer vehicles today, you can see something called adaptive cruise here. Basically, adaptive cruise is where when you drive behind another vehicle, it'll automatically adjust the speed, and it will reduce the speed or increase the speed to what you set to. So it's cruise control is the first one, but now adaptive cruise is where it can do the braking also. So now you can see that the throttle is working with the braking. So there is a combined function automation. So these vehicles are already coming up in production. It's already there in most of the newer vehicles now. That is what we call as level 2. Now, level 3 is what we call as limited self-driving, where there is a limited level of self-driving. If you take a vehicle like Tesla today, there's something called autopilot. And in autopilot feature, there is an integration of braking, throttle, and steering. It drives by itself. But you need to be there in the driver's seat with your hands on the steering. But it can take care of driving by itself in, say, highways and stuff like that. So it's still there is a need for a driver there. The driver cannot sleep, or driver needs to hold his hand in the vehicle. So driver is expected for occasional control. It cannot do everywhere. So this is what we have today. And as I see in future for next 2-3 years, you will see lot more vehicle which has this features of autopilot. I think a lot of GM vehicles and the Ford, which is coming up next year, is going to have these kind of features. in auto, which is called autopilot, which is called limited self-driving. Now, every industry, every OEM, which is coming up, are all working on to what we call as level 4 or level 5. Level 4 is where we get full self-driving. That means integration of braking, throttle, and steering. Driving not expected for control. The driver needs to not control the vehicle. Responsibility of for the safe driving and monitoring and making sure that every system is working properly solely relies on the vehicle. So that's where everybody is trying to achieve that full self-driving capability in our vehicle. So, but it'll evolve eventually, but it will take some time because there is a lot of more, little more areas where we need to make sure that you are able to take control or safely handle such situations like weather and bad weather. But people are all working towards that, so it's going to be in future for sure. Now, to reach that level 4 or even level 3, your safety level in your system has to be much more than just fail safe, wherein you just shut down the system. So that's where, like when we are working like a steering or braking suppliers to vehicle, we have to architect our system such that we are able to work towards that level of autonomy. That means we have to design our system which are fail safe now to a fail operational. That means systems shall operate with full capability even after a failure. So that's how we get safety increase for making sure that level 4 or level 3 autonomous is possible. Now, when you talk about safety, the first important term when you design safety or when we try to understand how to design, you cannot design all your parts. You need to understand, first of all, which are in your, say, taking care of steering. Even in steering, which parts is it electronic? Is it mechanical? Is it software? Which is more safety problematic? So that's to understand which area we need to work the most first so that we can make it fault tolerant. We give something called a rating for each part of it. And that's what is called as fit. A fit means fault occurrence rate measured in per billion hours. That means the higher the fit rate number, that means that part is prone for a failure in vehicle. So the idea for us in our design is to identify the area where the fit rates are high and try to work them to make sure and define and design the architecture such that you can bring down the fit rate by adding redundancy or making sure that there are multiple ways to reduce the fit rate. So making sure that we apply all that stuff when we architect the system. So the fit applies to electronics, it applies to mechanical, it even applies to software. Everything is there. So it's a whole complete system. So safety goal, our goal is when we define a system is to lower the fit rate with various design options, thereby increasing the availability of the system. That's our goal, what we are planning to do, going to increase the safety level. Now, so you can quickly see that when we go for full autonomy, each and individual system in our vehicle has to have very low fit rate. That means even after a failure, the system can work properly. That's the same concept we are trying to bring. Now we know what we need to do by looking at the fit rate. We need to bring down the fit rate. That's our idea here. Now, if you take a system, you can quickly see there is especially if I take autonomous mechanical system or mechatronic system, there's a mechanical area, there's a hardware, there's power electronics. So what do you do for most of these areas? Mechanical is usually covered. How do you bring down a fit rate of a mechanical system? Like if you have a gear and if you have a ball screw and all that stuff, how do you bring down the mechanical fit rate? This is usually covered by the design margins when you design the system. Like you have a larger margin and doing various kind of DFMEA means design failure analysis and making sure that in the given operating range, we have a margin of design so that the system doesn't fail. So breaking of a gear is usually not happening in our vehicle. So that's how the fit rates of usual mechanical systems in reality is much lower compared to power electronics or software or hardware failures. So mechanically, it's the way we look at it to bring down the fit rate is by having a larger design margin and making sure we test the system throughout extreme conditions and stuff like that. and making sure the mechanically it doesn't fail. Now, yeah, I wanted to show you guys an example based on a case study taking electric power steering as an example to show how we what we can do to design options are there in motor drives and power electronics in the case of increasing the decreasing the fit rate or increasing the safety level. So I'm going to take electric power steering as an example here. Before I start on electric power steering, I just wanted to show you what electric power steering means so that everybody understands what it does. And then I can then talk about what we do for various failures in electric power steering. So electric power steering, as you guys know, in this picture kind of visually grabs the most important part of what electric power steering does. Electric power steering is basically assisting the driver while he is driving the vehicle in steering point of view. So basically, what we do in electric power steering is the first thing is the steering wheel is where the driver interacts with the vehicle. So basically, we have something called a torque sensor in here where we analyze where we sense how much torque the driver is providing while steering. Once we sense the torque, we send that signal to our controller and the motor, which is in the rack. This is the rack which steers the vehicle. The controller senses the amount of driver torque the driver is putting, and based on that, the motor is now going to assist him to steer the vehicle. That means the driver has to put a little force. The motor will do the rest of the job steering the system. So there's a controller here. The controller senses not only the torque, it has to drive this motor drive system. So motor needs to be sensed, motor position, motor current sensor needs to be sensed by this controller so that it can drive this motor to assist the driver. And this is what we call as rack and pinion gear. And basically there's a mechanical linkage between the motor and this mechanical system. So motor is going to rotate, which will make this translation motion in here such that it assists to steer the vehicle, the wheels and stuff like that, so that the axial force comes from the motor plus the driver. So that's the idea behind the electric power steering here. Now, I just wanted to show you just electric power steering gear by itself. You can see that there is a torque sensor, then there is a controller, a motor, and then there is you can see now the inner part of it. I think I have a better picture here. There's a belt from the motor. This is the motor shaft. Then there's a belt pulley system, basically using the rotational motion of the motor to become a translation motion here to move the gear this direction so that it turns the wheels. So that's the idea of electric power steering. Now, from a control system point of view, what we usually do to drive the motor is usually this picture you would have seen in any major control system books while you guys are learning is basic, simple current control system. So you will have a current measurement circuitry. So we need to have a current sensor. We need to have a position sensor. It's a three-phase motor, usually what we use here in electric power steering, because it's usually a permanent magnet synchronous motor because of the current density, torque density you get for the packaging, because our packaging needs to be small. So our motor needs to be small and it needs to provide a lot more torque for that area. So that torque density is higher. So basically we have a current sensor, we have a position sensor, we then sense, and then we'll basically have, it's an open loop torque system. So we read this torque command is coming directly from the basically driver's torque and how much torque the motor needs to assist based on the driver torque. That's our torque command. So from there, we kind of create the current reference, and then we have a PI controller, and then it applies the duty cycles to the inverters. And then there's a three-phase inverter to drive the motor. So this is what internally how we drive the motor drive system. Now, failures on EPS. So what all type of failures you can expect? You can expect a sensor failure. There's a power electronics failure, which is called inverter failures. And there's connectors and communication failure, software failures. And then we move on to more of mechanical and other environmental failure. Then there is motor winding failures, hardware failures. Then we come to mechanical failure, which we call as belt skip or eye shaft. So as I showed you before here, there's a belt between the motor shaft and the rack and gear. that can slip from the motor. So then the motor torque won't be applied to the system. So that's like belt skip. And motor mechanical failure, which is like rotor shaft braking. This order you can see here, I've done it in the based on fit rate. So you can see that a motor shaft braking is highly unlikely and the fit rates are already lower because of the design margin we have. While a sensor failure is very, very common and the fit rates are much higher there. So the goal for us is to identify that area first. So we're going to work on this area to architect here so that we can bring down the fit rate of these systems. So that's the basic idea behind what we are going to do, how we are going to architect our system. Now, as you all know, aviation industry already are usually ahead of automotive industry in regards to safety. So we can learn a lot from aviation industry and understand how they have done to kind of understand what we can do in automotive also. Some key points I've plotted here is that a single point failure in the system during a flight should not prevent a continuous safe flight and landing or reduce any capability of system. So this is what we are going to achieve, that any single point failure in automotive industry is not going to bring down any of our system down. Or for doing that, using a redundant or a backup system to enable continued function after any single failure is one of the strategies, which is the strategy which they use in aviation, which is what we are going to use similarly, but we have other strategies too, but mainly redundant and backup systems. Isolation of systems and components and elements so that the failure of one does not cause failure of another. So that's what we want to make sure that when we design or architect the system, that any failure is independent. There's a lot of independence and it doesn't create multiple cause of other failures. So we need to have independency, proven reliability so that multiple independent failure doesn't unlikely to occur during same flight. So we should make sure that we have tested or we have made sure that there is multiple failures at the same independent failures doesn't happen at the same time. We don't want that to happen because then you have dual point failures at the same time, which is also not a good system. Failure or warning indication to provide detection. So immediately we kind of provide warning and indication to the driver. Checkability, the capability to check the components detection. Design failure path. So even during a failure happens, we should make sure that after a failure, it follows a safe path so that a driver can move the vehicle at least to the side of the road so that he is not in a safety area or in a what do I call as in an accident prone area such that he cannot do anything. So we need to have a design failure path. The other one is the error tolerance. That means considered adverse effect for foreseeable errors during airplane design, test, and manufacture. That means we should have enough margin in each and every portion such that there is a good error tolerance in our design. Now, strategy ahead is what we are trying to work for level 4 autonomy is that a single point failure doesn't do any degradation of the system. And after a single point failure, if a dual point failure happens, that's where we will have a partial system. That means a reduced performance system. And then a triple point failure is what we need for complete system shutdown. So we believe that if this kind of strategy is made possible, then autonomy wise, we will be much safer system because as soon as the single point failure happens, we will detect it. But the driver will not have any performance reduction, but we'll start to give the warning signs. And then there's a dual point failure. So there's multiple times it can happen by which the driver will be in a safer condition, even in a fully autonomous vehicle. So that's the key strategy going forward from our for the level 4 autonomy. So strategy to lower the fit rate, there are two main concepts here, which we kind of making sure that our industry is employing, which is called homogeneous redundancy and diverse redundancy. As I talked before, aviation industry, they were talking about redundancy. There are different types of redundancy which we can do. So a homogeneous redundancy is a system where there are two identical instances of the calculation. That means there are two identical sets of this thing. That means there are two ECUs, identical calculations happening on both the ECUs. So if one fails happens, it will just switch to another one. So thinking about the sensors, you will have two sensors basically. If one fails, it will automatically switch to the another one, which is exactly the same thing. Now the problem with the advantages of homogeneous redundancy is that you have reduced development effort because you're exactly copying the same thing. So you don't have to worry about, say, same problem. You just have to duplicate the system. The disadvantage of such system is there can be a systematic failure. That means the same failure which happened here can happen in here, thereby taking both the system down. So a systematic failure is more prone to happen in homogeneous redundancy system. Now, the other type of redundancy is called diverse redundancy, where there are two components. Functionality wise, it's the same thing, but it's not doing the exact same calculation. That means there'll be two ECUs, there'll be two algorithms trying to work the same way to steer a vehicle, but they won't be the same thing. They'll be done differently. Their development will be different, such that even one fail happens, this other system will take over, but it's not the exact same thing. So the systematic failure is reduced in such systems. But the problem with such a architecture is that the development time is much higher compared to homogeneous redundancy. Now, what do you do for sensors? So I'm going to take, for EPS case, the major sensors used, as I told you before, is like torque sensor, motor position sensor, and current sensor. So we are going to look at what are you going to do for these redundancy for such sensors. Taking case of usual sensor, what we are doing is a dual redundancy concept. That means having multiple redundant sensing capability in the system. So take an example for a motor position system. You have a motor position sensor and a magnet which will assess the rotor position. This chip is going to basically read the magnetic field and understand where the motor position is. Now, this chip has two technologies inside here. The position one is basically calculated using something called GMR technology. The position two is something called AMR technology. So you can see that a controller, when it kind of receives two positions, which senses the same rotor position, but two different technologies. That means we get what we call as diverse redundancy here. So that's a concept majorly used for sensors in when we are architecting the system. So moving forward, all our sensors are capable of having multiple redundancy in them. And we will make sure that when we design our chips with our manufacturers, we'll make sure that they are defining such that there are two different technologies also inside the same chip. Now, is that good enough? Think about the case when you have dual redundancy, does not offer complete redundancy, since during the failure, it is not possible to figure out which sensor failed. So if you have two sensors and say one of the sensors failed, how do you make sure that is the right sensor to turn off? So there needs to be something called a voting strategy. So there needs to be something to vote for to understand which one is actually going to fail. That is it position one which actually failed or position two which actually failed? Now that needs to get into, like, we need to have something called a position three or a mechanism where we can vote between position one and position two. Now remember, the position one and position two needs to drive the motor. So their requirements to make sure they have the right resolution and accuracy is the same because they are going to drive the motor. Position three need not be that. It's just going to vote between the position one and position two to understand which one failed. So the third sensor can be reduced price because their requirements are lower. But even then, if I'm going to go for another sensor, it's quickly you can see that as I increase the redundancy, it is going to increase the cost of the system. So I need to be smart about how to do such an architecture. And that's where we see a lot of help from sensorless techniques. That means we kind of use sensorless methods basically to define, to diagnose which one failed. So sensorless area, that's a separate topic, but sensorless areas are coming in way for our motor drive system, especially in electric power steering, through this area. I know for traction drive, there are a lot of areas where people are looking to just drive it with sensorless. But in reality, when you go into production and when we have autonomous, you cannot just solely depend on sensorless area. You need to have sensorless as a backup system. So in reality, sensorless is coming in as a voting or a backup strategy here, which can diagnose which position one or position two failed. Now, effect of multiple redundancy, you can see that as you increase from a dual system to a triple redundancy, the first failure dependency, that means after a first failure, the reduction in performance is much highly reduced. That means the dependability of the first failure of having a single point failure, there's no issues to the driver or something. So Now, moving on, what we do for inverter. So there are different levels of concepts for inverter to happen. So one of the simplest concept here, which I'm showing here, is basically you have a motor, which is a three-phase motor, and you have dual inverters. That means there's dual inverters. That means you have dual ECUs, and then there's dual power supply. This is what we call as the non-diverse redundancy, where we have exact copy of each other. And basically, the inverter one is the primary inverter which drives the motor. And upon any failure on this system here, it quickly switches to the inverter two, and inverter two, which is EC2, will drive the system. Now, so inverter one supplies the full current, and EC1 has the logic to control the driver and diagnose any fault on its sides. Inverter switch 2 is only connected to the inverter 1 at this normal working condition. On failure on inverter 1 causes the inverter switch connect to the inverter 2 side. Inverter 2 is capable to provide the full capability, and therefore there is no degradation of the performance. Now, what is the pros and cons of such system? The system is able to provide full performance even after failure. Both system 1 and system 2 have similar application, thereby reducing the development effort, which we call as homogeneous redundancy. So it is the same set of code which is running on both. Now, the cons of it, such an architecture, you can quickly see that both inverter 1 and inverter 2 needs to be sized for full current, thereby increasing the cost. This inverter 1 is carrying the full current. This also needs to carry the full current. So your inverter, you need to have two sets of it where the cost of the system is going to go up. The two independent power supply needs to be designed so that it can supply the full current performance. Not only the inverter, now these two power supply from an OEM point of view needs to be designed for capable of driving for the full current. So especially in OEM, the power supply and the cable length are very key for cost. So they need to provide such capability so that you have full performance. Now, this is one type of architecture where people are going with in for full autonomy, because you get full performance even after a failure. That is the biggest pros for this kind of architecture. Now, what do you do for motor? Is there a better way to do for the motor? Now, for a motor, for redundancy of a motor design comes from winding sets. So basically, a single motor can have more than one winding set. That means there are two winding set or three multiple level of winding set. Therefore, even if a winding short happens, you can quickly work with the other winding set. You may not be able to provide the full performance, but at least you can quickly provide partial performance and keep on moving the system. Now, in the case of another way of doing it is basically you define two systems wherein each one provides 50-50%, or you can even provide 50-50% here, and therefore each of the system will be able to drive the system together, where we have dual motor actuation system. So any failure in the system, even with motor shaft break, you can still work with the other system to keep driving the vehicle. Now, another one which is quickly going is what we call as independent actuation system. This is where the new research is happening, where we are bringing, instead of having traction drive, a big motor, and to drive the vehicle, we want to bring the motor drive right at where the load is demanding for. So think about the way where we do motors directly at the wheels and the power electronics directly at the wheels. Then you automatically get different redundancy, because you will have four systems or two systems based on a front wheel drive or all wheel drive. You can have four systems where you get multiple redundancy in that case. This is where the newer research is happening, where the actuator is right at where the demand is. Now, let's consider the case from a controls perspective, the two-phase winding set. That means a motor which has two winding sets. How do we control such system? Now, for an EPS case I'm going to show here is basically system 1 provides 50% of the torque demand. System 2 provides 50% of the torque demand in normal condition. That means each side of it provides 50%. So there is a ECU here, there is a inverter here, there's another inverter, there's multiple current sensors on both sides and position sensor, but both are only providing the 50% of the current. But together they'll give you 100% of the system demand. The good thing here is that you can quickly see both these inverters are, though working at the same time, needs to be only defined for half the current load. That means the power supply needs to only provide the half the current. Inverter needs to be defined half the current. Thereby, we reduce the system cost. So now you can quickly see that you can define a system where both systems are working exactly at the same time. And you can have two different heterogeneous redundancy because two can work independently with each other and having different sets of code too. Now, upon a failure, the system 2 provides a 50 to 50% torque. Up to 50% torque is the only thing you will get. Therefore, from the other architecture which I showed before, in here, the system cost is less, but you only get 50% of the demand when upon a single point failure. That means if an inverter fails, you only get up till 50 points. So think about this case. In reality, in steering kind of a system, when you drive the vehicle, you don't need the full performance to generally drive the system. You only need the full performance when you're at a huge turn or like in a corner area where you are pulling towards the left, and that's where the demand goes up. While you're driving, usually when you're driving straight or when you're taking a small turn, you are much below 50% of the rated torque. So you can actually drive the system a long time, and the driver will be safe enough to drive it to his home or to the dealer to get it fixed. So these are most likely for different OEMs. They like it because the cost is less, and they get kind of the safety also because the driver is not left barehanded when the failure happens, and then he can still drive it to his home and he can still drive it to the dealership to get it fixed. Now, the pros with single motor with multiple phase is that inverter short happens in one winding set. Other winding sets can still provide torque to actuate the system. In the first case, when I showed you multiple inverter redundancy where we can provide full system, winding failure is one common cause failure in that architecture. In here, winding failure is not a common cause because even if you have a winding failure here, the other winding set is not affected. Thereby, you can still drive the system. The torque produced during one winding short is proportional to the number of winding sets available. That means if we have motor with two winding set, upon a failure of one winding short, we can provide max up to 50% torque. So think about it. We can increase from 2 to a 3 winding set system too. And thereby, the motor can provide 75% torque on failure. So when you increase to a 3 winding set motor, you need to have 3 inverters too. Thereby, each one is only defined for, say, each one is only defined for 25% or something like that if you have 4. So those kind of architecture is possible with such design. The inverter needs to be designed only for a 50% max current if it's 2 winding set. So the only major disadvantages you get is that all failures does not provide 50% torque, especially motor phase short and line-to-line short. Such failures are rare, but even in this case, it'll be little less than 50% torque. Need to have 2 independent inverter controlling the motor for normal operation. That means 2 inverters has to work at the same time for the normal operation in such architecture. Now, dual actuation system is another where we have 2 actuation systems. That means it's not just the motor. You have 2 separate sets of motor, controller, everything. In this case, 2 actuation systems are designed in the architecture. Each actuation system is designed to give 50% of the total system output. In normal working condition, both system is designed to meet 50%. In the case of failure 1 in system 1, system 2 shall provide 50%. Such an architecture does allow for heterogeneous redundancy. That means this whole system and this whole system can be independently designed by 2 different software, 2 different things, working towards giving 50% of the actuation total system output. So heterogeneous is possible in such cases. The other advantage here is that a winding short here doesn't affect this guy because it's 2 independent actuation systems. So thereby, it is little better than the previous architecture we showed you. But you need to have 2 motors designed for providing 50% output to the system. Now, as we move on to such systems where we have gears and mechanical efficiency, we quickly see that there's a good call for why we need to have such mechanical losses and stuff like that. That's where the independent actuation system comes, wherein actuations are not dependent. See, here also the gear is the same. So if I take that out and if I have independent actuation at the wheel, you can still drive the vehicle without having like you have multiple redundancy here, and but your demand and the actuation are right at the same place. In such architecture, actuation system is placed near the load demand, thereby reducing the mechanical gear reduction and efficiency losses. So that's very good in the case of failures and efficiency wise. We have much better efficient system. It provides heterogeneous capability as these two systems need not be similar. So these two are completely independent systems. You can design it different ways, just that they need to talk to each other when we are defining torque and stuff. But this can be developed totally independent each without each other. This provides system with more than dual redundancy because you can have four wheels on four wheels. So it provides more than dual redundancy. The required system output per each system is much reduced, thereby making the system smaller and easier to package. So that's another advantage when we reduce the system output needed by each system. The packaging will become much smaller. The system failure resulting in complete loss of redundancy is less in such system because you need to have four system failure happening, and that too not just single failure, it has to be multiple failure, which is very unlikely to happen in any drive. That's where you would have heard about something called in-wheel motors, where there's a lot of research going on now to actually bring this back. It was there initially, but there were other issues. But I think research is going towards in-wheel motors for independent actuation in each wheel, no transmission, so you don't need any transmission in the vehicle. Extra space for better vehicle design, because look at it, you have whole space here. There's nothing, no axle, no reducing gear and stuff like that. Ability to control each vehicle independently, thereby giving a better ride and handling. So you can quickly see that each wheel can be controlled independently, so that the turning radius of a vehicle can be much more improved in such systems. It gives you much better control to control the vehicle. Now, what is the cons? There are definitely a lot of challenges in such system too. Additional weights on the wheels will create what we call as unsprung mass, which creates a ride and handling issue when we go through bumps and stuff. But I think needs to be worked out. But this is almost been worked out now in industry. Should be durable since motor drive is inside the wheel. So now earlier the motor drives were at a better place where it was not affected by bumps and stuff like that. It was much more controlled environment. Now it's inside the wheel, so should be durable for that. In an event where one system fails, system should not create asymmetry conditions so that the wheel is not pulled to one side. So any condition, if any fails happens, we don't want the vehicle to move towards one side, getting pulled or locked in one system. That is very bad when we are driving. So we need to take care of such issues in such architecture. Now, it's not only all these motor sensor, traction, inverter, motor architectures that we have redundancy. It even goes to the point of designing the ECU or MCU. Now, as we go in the newer chips we have here, we can quickly see that there are dual core systems which we are using in our microprocessor when we are defining microprocessor or designing microprocessor. There's a core and core 2. Each is defined by the single its own power supply. So there are two independent systems. We have two different cores. Or another way is that this is inside one common die. The other way is that there is a main core and then there is a supervisory core which talks to each other, which is outside two dies. They're like two chips. So dual core with two separate chips communicating using SPI. That's another type of architecture. Now, even in a multi-core MCU, you can see that the CPU are independent and they have their own safety mechanism. Each safety mechanism is independent for each CPU. So you can see that there's a watchdog for each of these MCU independent of each other. Not only independent on inside one die, there is an external watchdog to make sure this whole MCU is working too. So that's where we call as heterogeneous redundancy, where we have independent actuation not only inside the MCU but outside the MCU also, to make sure that MCU is working properly. Now, I am coming towards closing down of how we basically define what is the right architecture for you. I showed you many architectures here. What is the right architecture? So the basic concept lies in these main points here. Redundancy of components to meet the fail operational requirement, but at the same time increases the cost of the system. Therefore, you need to understand how much redundancy do we need and what level of performance do we need on upon a failure. Each OEM has different ways of thinking about it. Some OEMs thinks that they need full performance. Some OEM thinks that they only need up to 50% based on, I'm talking about steering or traction drive, depending on different systems. You need to understand what is the fail operational criteria, how much performance you need. Based on that, you need to define your architecture such that though you're going to increase the redundancy, you need to be smart about keeping the cost down. The amount of redundancy add needs to be decided based on the required performance during failure and the safety goal of the system. The redundant architecture chosen should meet the safety requirement. That's the main goal. What is your safe case and what is your safety requirement upon a failure? That we need to be met by using the redundant architecture. In case of sensor redundancy, it is important that you use techniques like sensorless estimation, as it provides extra diagnostic capability without any additional cost. In case of motor design, the design needs to be chosen such that the system will provide adequate output upon a failure condition, thereby meet the system performance. It should be noted that common cause system failures, which remove the complete redundancy, needs to be carefully analyzed. So in any system, the main problematic now when we have redundancy is the common cause failure. You need to analyze those areas. Say for a full performance, as I showed you before, where we have inverter 1 and inverter 2 capable of giving full output, motor failure is a common cause failure because you have only one motor. So you need to analyze those areas. You can have multiple windings there too, but you need to analyze such concept and understand the common cause failure and bring down that fit rate, making sure that by design also, motor failures are rare compared to sensor failures. So you need to understand that and take the risk and understand those, carefully analyze those areas. In general, heterogeneous redundancy is better because you have two different systems designed differently but achieve the same functionality. But the problem with heterogeneous, as we see right now, is the time to develop the system. So I think what's happening right now is we start with homogeneous, and as we keep improving, we move towards heterogeneous redundancy is what is happening in our industry right now. Now, I've talked about all about safety and safety architecture. The last two points I want to make here is various new system which is going to come up in future for driving the vehicle is what I need to show here, especially for a fail mitigation technologies. That means the best way to avoid failures is never get into a failure condition. And usually if you see the records, human failures are the main cause, human errors are the main cause for an accident. That's very high. Therefore, there are a lot of concepts here which we are bringing now, how to reduce that kind of error. Thereby, we are not getting into a failure condition. That's what we bring in by, we already have ABS, we have backup camera, we have forward collision, lane departure warning, lane keeping, autopilot. These are different types of features we have in the vehicle such that the driver interaction is less, the vehicle is taking control, and you don't get into an accidental situation. So prevention is the best method. So there are a lot of mitigation techniques before entering there. So the most effective form of mitigation is to provide, earlier was to provide crash avoidance technologies like these. That was the most effective form of mitigation. Now, that's where the new architecture is coming, what we call as drive-by-wire systems. That means drive-by-wire technologies replaces directly the mechanical linkage between the driver and the various car elements with the electronics component. The electronics does most of the safety critical functionality in such architecture. Although the mechanical systems are powerful, they become overly complex and inefficient and conducive to wear and tear over the years. Mechanical systems they have a mechanical link to the driver, so the driver is in the loop. Now, advantages of drive-by-wire is the elimination of mechanical parts, reduces the weight of the overall system, thereby your miles per gallon improves, or fuel kilometers per miles per hour gallons improves fuel efficiency, more space available for better car design, lowers the manufacturing cost, steering response can be easily adjusted, reacts to more quickly, resulting in shorter stopping distance because the controller is taking care in case of you get into an emergency. So the driver is not in the loop, driver is cut off, and then the system can act much faster than the driver can act. So the main three drive-by system right now in our industry, which is being researched a lot, is what we call a steer-by-wire, which is for steering, brake-by-wire, which is for braking, and throttle-by-wire, which is for throttle systems. Now, what is steer-by-wire? In traditional EPS, as I showed before, a driver steering is mechanically connected to this gear, which is driving the vehicle, steering the vehicle and the wheels. Now, in a steer-by-wire system, that mechanical linkage is thrown out. And basically, you see that a driver is not directly connected to the wheels. It's basically, there are two actuation systems, one to actually drive the vehicle, one to provide the feedback to the driver. This is what we call a steer-by-wire system, in which case you have two motors. One motor is to drive the vehicle. The other motor is a smaller motor to provide feedback to the driver. And so that it's not very, because there's no mechanical linkage, there's no load, we need to make sure that the resistance is provided to the driver when he drives the vehicle. Now, from a controls architecture point of view, you can quickly see that the one on the top motor on the top is basically what we call as a torque control system. The feedback from the driver from the bottom, which we call as the actuation system on the road wheel, is what is fed back as a torque command to the system here. This torque command will then apply a resistant torque when the driver is rotating. Here also you can see that instead of measuring when the driver is rotating the steering wheel, earlier we were measuring the torque. Now we are going to also measure the angle of how much he has turned. Once we know the amount of angle the driver is turning, we give this angle command to the bottom motor. And basically the bottom motor is now in an angle control rather than a torque control. The angle, basically the wheels are moving towards that much angle based on how much driver moved from the top. So driver is not mechanically connected to the system. We sense the amount of angle the driver is providing. And based on that, we give the position command, and this motor turns this wheel towards that angle. On the feedback point of view, we have a force sensor or a force measurement, which provides how much force is being applied, which acts like a torque command onto this system, which provides a resistance torque to when the driver is moving. That means he feels as if the driver is pushing the wheels, and he makes sure that he doesn't feel weird. If I don't provide anything, it'll be very easy for him to turn quickly. So we provide a resistance torque on the up so that the driver feels like he's moving the wheels. In steer-by-wire, the road wheel actuator needs to be in position control. The system control is to maintain the steering wheel position to a desired angle. The base torque control system now shifts to a torque position control system. Earlier, I showed you this diagram for EPS. On top of that, now for the road wheel, where the position control is added, you quickly see that there is an angle control also adding up. This was a torque control, which was a current control inside. Now we have an angle loop and a velocity closed loop, which acts to provide the torque. So that's which happens in the road wheel now. Now, the same thing is true for an electric braking. So we are also going to provide like brake-by-wire, where the motor is going to actually brake the system. Earlier, as an evolution of brakes, we started with the hydraulic brakes. We moved to an electrical brakes right now, and we are truly going to a true by-wire. That means brake-by-wire system in future. That means a motor is going to actually apply the brakes to you on the calipers, such that the calipers are moved towards braking the system by the motor. And the motor gets sensing from the pedal position, which the driver is applying. Thereby, he knows how much torque he needs to apply such that he can apply the brakes. Now, brake-by-wire architecture are very useful because now you have a master braking system, and that provides each individual corners with their braking torque needed for the motor, and the motor actually brakes the system. Now, the advantages of such system is that they increase safety by decreasing the stopping distance up to 30%. So you can stop faster now, because as soon as you apply, we actually apply the actual braking much faster by the motor. Undesirable feedback. So if you look at today, you'll have feedback based on the road wheel and stuff like that, which is undesirable for a driver when he's placing the brakes. We can provide a better feedback system because he's not actually connected to the brake system. So we can provide a better feedback system. Reduces the brake pad wear, because now since the motor is actually applying, we can make sure that during emergency, the right amount of brake is applied and can be brought to a narrow position, thereby reducing the actuation time so that the wear on the brake pad is less. The better control of all brakes with respect to the driver's intention can be given, because in mechanical system, the driver has to do the work, but here based on that driver's intention, we can actually provide a better braking system. Driving comfort can be increased by lowering the pedal force. You don't have to floor your brakes to brake it faster. We can reduce that by driver providing less force, but we can actually apply the true force in the, which is because we can tune the pedal feel such that the actual force is applied, which is useful for a lot of drivers because they're not applying the right amount of brakes today during an emergency condition. Main challenges need high redundancy. I'm just going to go over this. Like you need high redundancy, therefore you need highly tolerant systems. Key redundancy for most sensor and actuators is needed. High speed, fail tolerant communication is needed because you have to communicate back fast enough so that you can apply the brakes or you can change the steering angle. No, so that increases the voltage power, or we want, because that if you're integrating brakes and steering, it's better to do at a higher voltage. Therefore, the current is less, so that their cable, because the cable length is going to be larger now because you have to communicate that further to the actuation system. Therefore, increasing the voltage will reduce the amount of current through the wires. So that's idea. So higher voltage chipsets is needed. Higher redundancy in sensor, power chips, and microcontroller increases the cost a bit. High redundancy requirement means higher end MCUs are needed for such application. High degree of availability of complete system is required as there is no mechanical fallback. So since there's no mechanical fallback in such system, you need higher availability of the system too. And software systemic failures like erroneous MCU behavior needs to be addressed, as such faults might propagate into a total system failure. So we need to understand that completely before we are doing such kind of system architecture. So these are, though I talk about a lot of challenges, they're actively working in industry to address all these issues. And there's a lot of interest in moving forward with such architecture in future. So conclusion of my presentation is that safety critical in automotive needs provide more availability for future safety needs. Redundancy helps to bring down the fit rate. These are the key points I kept on talking in this. So redundancy helps that. Amount of redundancy is analyzed by the safety goal for the system and performance required during a failure condition. That's a key point here. You can have different type of architecture based on what you need. Heterogeneous redundancy, as I told you, is a better system, but homogeneous are easier to develop because reduce time for development. Reducing the mechanical linkage and having actuation system right at the loads will increase overall system efficiency and will be more fault tolerant. That's another key point here. Redundancy should be given in places where the failure occurrences are higher. That's very key here. You don't want to just define a system where you increase redundancy for system where the failure conditions are already lower. So you want to attack the right area. Redundancy should be given only in the places where there are higher fault occurrence. For faults like rotor shaft braking, we need not have considered as higher occurrence, as such faults are very low due to efficient design margins and DFME. Adding redundancy means more computational power in the processor is needed, and the development of MCU should take into consideration of reducing the systemic failure. So we need to make sure our processor power is good and there's dual cores and the systemic failure doesn't happen. System architecture shall provide a safe state in the event of such unseen failure happens. So even if failure happens, we need to make sure that there's a safe way for the driver to at least move to the side of the road and stop his vehicle, even in such cases. So we need to make sure that architectures are provided. So I think that's all I had. These are my references for my presentation here. I hope any questions, I'm open to any questions right now. I hope you guys understood that some of it from the presentation here. Thank you. Hello?
Okay, thank you, sir. Anybody has any doubts? I think no doubts. Thank you for your insightful talk, sir. On behalf of IEEE CUSAT SB, I would like to express our sincere gratitude. And also, I would like to thank all the participants for making this event a great success. Thank you all.
Yep, thank you, everyone, for the opportunity too. And I shall send this presentation, Basil, to you, where you can provide to everyone. I know there's a lot of things I've talked about here. When you guys go through it, and if you guys have any questions, you can always shoot me an email. and I'll be try. I'll help you to do my those questions. Okay?
Okay, sir.
Thank you. Thank you, guys. Yeah. Bye.
Ơi, đang to, mình đền. Hả?